proof by deduction. So we have to prove that if the perimeter of a square is the same as the circumference of a circle, then the circle has a greater area than the square. So we first look at perimeter and circumference here, and then we look at the areas afterwards. So we have a square of side x, so if its area is x squared, its perimeter will be 4x, and the perimeter is equal to the circumference, is the same as, which is what we're doing here. So 4x for the perimeter, circumference 2 pi r. So r is equal to 2x over pi. Now we move on to the area of the circle, pi r squared, but r is 2x over pi, and then simplifying. Now if the area of the circle is greater than the square, if I divide the circle's area by the square's area, I should get a value that's more than 1. So area of circle divided by area of square here. So the circle area is right there, and I'll put that in here. The square is just x squared. Okay, we simplify, and 4 divided by pi is a value that's greater than 1. So the circle has a greater area than the square. Prove the sum of the first n natural numbers is given by this formula. So here's my series: first value, second, third, fourth, and so on until you get to the last one, which is n. Now I'm going to reverse the order of this series, like so, and then I'm going to add these two together, these terms, these terms, these terms, these, and so on. So the sum of both series is given by these terms, and you can see that these terms add up to n plus 1, these two add up to n plus 1, as do these two and these two. So how many lots of n plus 1 do we have? There are n lots of n plus 1. So the sum of both series here, these n plus 1s, they all add up to n times n plus 1. But we've added the series twice, so we have to halve at the end. So the sum of just this series, this single series in this row, which is what we're doing here, is a half times n into n plus 1. Okay, we're proving that if x minus p is a factor of f of x, then f of p is 0. So we can write f of x as the factor times other x terms. F of p, that means x is p, so we substitute in p for x, so here, here, and here, like this, and we can see that this is 0, and 0 represents the remainder, which means that x minus p is a factor because the remainder is 0. This is basically the factor theorem. Prove that any odd number can be written as the difference of two squared numbers. So we have odd numbers and the difference of two squares, like this. So 3 is odd, and 2 squared minus 1 squared will give 3. And we have a difference of two squared numbers. Same again, odd number, two squared numbers, and again, and again. But this only proves these numbers. Is it true for any odd number? So we use some algebra this time, and the reason for choosing n and n minus 1, you've got 2 and you've got 1, 3 and 2, 4 and 3, 5 and 4, n and n minus 1. We're just following that pattern there, expanding the brackets, simplifying, and we can see that 2n minus 1 is an even number minus 1, it's therefore odd, and we've proven this.